is Kaixin from Fudan University. We'll talk about 2D CFT factoring at the boundary of the topological field.
Yes, thank you for the kind introduction, and thanks to organizers for putting up such a lovely conference. So today I'm going to talk about recent progress of generating some CFTs from any given spherical fusion categories. So the basic motivation is like this. So we know from very early on that every rational CFT gives us some modular tensor category as a description of its vortex operator algebras. But people still don't know if every modular tensor category has RCFT realization. So a very famous example is given by the center of the Hagraph group we're going to talk about. So people don't know if it has a rational CFT realization. And on the physical side, there is a trending on interpolating between the topological and the QFT series. Now people call it sim TFT, but it's actually we have so actually from last century, people know that at the boundary of Chern-Simons theory, we have some kind of CFTs. And what I'm rather more interested about is interpreting this quantum field theory on some kind of lattice, so I can really put this into our computer to work out rather than doing some integrals. So basically, that's my personal motivation to do that. So in case I use up all my time talking about introductions, I will first make our claims right at the beginning. So from any fusion category, we know that its phases is described by all kinds of Frobenius algebras. We'll call this A. And it will make it more clear later, but let me just first state it as it is. So we know that from every A, we can construct some boundary states. And we claim that purely from categorical data, we can construct this kind of boundary states. And we claim it is the phase transition between these two phases. And the second thing is that we can predict if we want to interpolate between more phases, we know that there's some phase boundaries, and we can predict large part. Please.
So you said A sub I is a Frobenius algebra.
So it's just some random Frobenius algebra, any two. Yeah. So we will show later that at least in our construction, every Frobenius algebra gives us a gapped phase boundary. And this basically describes the gapped phases it's in. So at least in our construction, it is true. And Zhao shows that actually it's true for many more cases. Please. Sorry? Actually, in our construction, we believe it's not true. We believe there are different phases, even between Morita equivalent Frobenius algebras. So we can show later. And maybe our so sometimes people talking about 2+1D phase boundaries, and we are actually talking about some 2+1D phase boundaries. Maybe that's the difference between here, because I always hear people saying this kind of thing that different Frobenius algebra corresponding to the same phase. But I think there's some nuance here. Maybe we can discuss later. But I will show you that in our case, between every pair of Frobenius algebra, there's phase transition. And it's mostly many of them are second order. What is? Oh, it's just some number of lattices. It doesn't really matter. We will show this later. I just want to kind of give you a hint of what is going to happen. And second, we can predict large parts. Yes, 1+1D. Or you can say 2+0D. We can predict large parts of the phase boundary. large we mean that near the trigonal point, or there's some twist.
Here, model one part, one basis and this transition.
Yes, yes.
I guess you assume some symmetry of the system.
So it's described by the category. The symmetry is described by the category I put in.
So you do have symmetry.
Yes. Yes, yes, yes. So I think it's actually this categorical symmetry forced the phase boundary into CFTs in many cases. Oh, I have to. Third is maybe too strong, but so we didn't actually write the third argument, third claim in our paper, but I think maybe it's true to most cases that the resulting. So here, sometimes it's first order, sometimes it's second order. If it's second order, we believe it's a CFT. And we claim that for these resulting CFTs, its modular tensor category has a subcategory that's given by the common ancestor of these two forbidden algebras. That will make more clear what is common ancestor. Sometimes it's just the category we put in, but sometimes it's subcategory. So is it all clear what we are going to get? One word for Hagar. So we didn't really get a CFT with Hagar symmetry. We don't get a CFT with its modular tensor category being the Hagar, being the center of Hagar. But we do think that our resulting CFT has a subcategory being the center of the Hagar. But it's physical argument. We don't really do any proofs.
A subcategory.
Yes, yes. I will make it clear later. So, sorry? So we. Oh, yes, sure. Yeah. So in some cases, in Hagar cases, we do have this C parent being the Hagar. So actually, in any kind of categories, we can always choose some. We can choose different forbiddance algebra to compete, and they have different subcategory being here. Sometimes it's the category itself. Sometimes it's the subcategory of the input category, and
It's like this CC parents in the Hagar case. You're saying that you'll have like some set of primaries that are closed under fusion that realize this Drinfeld center of H3. Or,
yes.
So not the full thing, but just some closed subset of subcategory of primaries, basically.
Yes.
Okay, that's very interesting.
I'm not sure it's mathematical rigorous. It's some physical arguments. Yes.
But it's not a hard CFT.
Yes, I think it's.
With some they claim that if you have hybrid CFT, the sample charge would be 24. Oh, with Terry Gannon's or something. Yeah, I shared the house with him. 24. It has, yeah. I mean, if it's double, it has to be something like this. So they pretty bad, man. Certainly, what you see here is not has not using them for as much.
Yeah. We get much smaller central charge. We don't really get a Hagar CFT. We get something has some part of Hagar symmetries.
I mean, with CC parents, presumably is a modular tensor category itself.
So sorry.
I mean, CC parents is a modular tensor category.
Yes,
itself,
yes.
And so then there's just a general theorem of Muger on the structure of modular tensor categories that says that this is a factorized as a product, right? So in some sense,
yeah, maybe I'm.
okay, but the CFT doesn't have to factorize it. C is itself. No, but it's modular tensor category definitely factorizes. C is well, yeah.
C is not.
Which one?
C is not one.
No, but Z of C is minor. Yeah, but then that's Z of C will be a factor. There's a parent MTC, there's a sub MTC, which is an MTC, then a factor. Maybe not the level of CFT. In general, it won't factor. No, but if you have a modular subcategory, category does factor. Oh. I'm just saying that at the level of modular tensor categories, what they're claiming is they get the Haber of ZH3 times something else. But the CFT it may not factor. You mean this side? Yeah. Yeah.
Yes, sure, of course.
I think it's very hard to check if it is indeed so I suspect that they might have something matched, but there's some subtle data.
Yeah, maybe. So it's not a very strong claim. It's just some physical arguments. So let's get started. First, I will introduce some basic math I'm going to use. So we are using the spherical fusion category. And we would like it to be unitary. In general, I think we don't need to, but it makes our life easier. So it has some objects, and this object can be decomposed into irreducible ones. And these irreducible objects are called simple objects. So we have simple object A, B, C, etc. It belongs to the irreducible objects of this category. And they can fuse together to get something else. And its fusion is given by this rule. So if NABC is generally greater than 1, we need to put some label here to indicate which fusion channel we are using. But I'm not to go into generalize to that. I think it's basically doable, but I'm not going to talk about it today. And there is some association rules between these fusions. So basically, you can have two. Let me do this way. So basically, you can have two ways to fuse three objects. And they are differed by a symbol called F symbol. For fixed ABC, it's just a matrix to do the basis change. But in total, it has 6 labels in the simple objects. So there's something pretty nice about these F symbols. So they have Pentagon equations, which basically comes from the ambiguity when you when you fuse 4 objects. So it gives you the Pentagon equation. Basically, it's something like this. I'm not going to write the detail here. There's some label E here. And we also need the unitary condition. Basically, it says that basically it says something like this. And with this in mind, we can construct a topological field theory. Basically, we are using the Terra-Vera Barrett-Westbury construction. So given any closed manifold, we can triangulate into many different pieces of tetrahedrons. So a tetrahedron has six edges. So we label all these edges with a simple object. And by that, we can assign some weight to the tetrahedron. We just assign the F symbols. And with the pentagon equation at hand, so we can basically do some retriangulation of the tetrahedrons. So for example, if we have 2 neighboring tetrahedrons, it can be made into 3 with these pentagon equations. And also, when you have 4 tetrahedrons, you can make it into a 1. So basically, it generates what we call the Petrel moves. So given this partition function of the topological field theory, given this kind of partition function, basically, first we product all the weight given by a tetrahedron. And there is some other quantum dimension here. But we will mostly forget about other quantum dimension here. It's some technical detail. And we sum over all the allowed configurations. So this allowed configuration is actually imposed by this F matrix, because if the fusion rule doesn't match, it's just 0. So we don't actually summing over that kind of configuration.
The sum of the object
on the edges, yes.
For each tetrahedron, you replace something.
Yes. Yes. Basically, we have okay. So is it clear? So then you can. Mm-hmm.
So that the A, B, and how do I remember which is which? Is like if I look at the tree diagram, A, B, and C, the A, B will be connected to E. But in this figure.
So I can actually put some arrows here. I think I write it the right way. So these A, B, C are on the same faces. There actually we should put some home space on the faces, but I didn't write it. So basically it enforces that AB fuse to C. And this part is BFD and this part is CED. They enforce some fusion rules that you can actually check from here. So you can see that EC fused to D, and here it's ECD. And BC fused to F, and let me make it more clear. Sorry? You can pick any category, any spherical fusion category you want. Basically, there are many choices you can take. Oh, yeah. In CFT, basically, these are primaries. Oh, of course. Yes. Yes, it's an input category that we put on the. Yeah, so the excitation of this topological field theory is actually described by the center of the input category. Yes. I'm not so familiar with. Okay. Yeah, not module tensor category. Okay, I see. Yes, sure. It's actually AB. So I think it's right. So AB, if I didn't write the arrows, but if you add the arrows, it actually enforces the correct fusion rules. So ABE is on the same phase. Here is ABE. BCF, here is BCF. And ECD, AFD. ECD, AFB.
Oh, I see. So the rule is that the phase will be the vertex.
Yes, it's
A, B, and E.
this only gives us the definition of the F symbols. Once we are here, we can just forget about its definition. All we need is the F symbol. It tells you everything about the topological field theory. Yes, but if you want to make sure, yes, the fusion rules are correct. Okay. Okay. Okay.
CFT, right?
Yes.
So that line, the interpreted axle, basically the defect. That's the same as the one model.
But I guess you will go to stigma.
Sorry?
You will use this also to stigma.
Yes, screen nets. Yeah. Yes, we have screen net at the bulk. Sure. Yes.
So if I
Yes. You can triangulate any manifold into tetrahedrons. Yes. Maybe I'm not so sure about what link is. Yeah, maybe I'm not so sure how to do that. So now we want to put it on open manifold. Basically, we want to have some boundaries. So there's slides I can show here. Basically, we are consider something like this. So we are triangulating some open manifold, say that a 3D ball and it's full of tetrahedrons. And on the outside, it's basically a sphere, and it's triangulating into all the triangles. So now let's make it into a 2D. Now let's see that on the 2D sphere, so we can write everything more clear. So basically, this is a boundary triangle, and there are some lines pointing into the center. And we are going to write it as this kind of things. And everything has some label on it, has some symbolic labels. And so we choose a particular triangulation of the sphere, basically something like this. Oh, sorry. And we basically consider a very large lattice. And so it actually depends what you want. You can put any boundary condition you like. So when we are calculating a CFT, we are basically consider two torus. And you can also consider infinite dimensional, infinite large lattice. It's also okay. Yeah, so you can just take this as unit cell, then it's okay.
So we have the previously we have something in 3 dimensions, but
Yes.
push it to 2 dimensions. Where's ABCD first picture?
Yes, it's here. So these are red levels. It's here. So I just take a more clear picture of it. Then it becomes actually a 2D lattice. So it's basically the same thing I just showed in the slides. So on the boundary, we have blue triangles, and it has some vertex. This vertex is reaching into the inside of this ball, and these are the red lines we are drawing here.
And you have only one side.
Yes, because they're topological, actually. Sorry?
All other sides.
But we are actually labeling the links. Yes, but if we're talking on vertex, yes, it is. But we're actually labeling the edges, not the vertexes. And because it's a topological theory inside, actually you can manipulate it into other kind of things. It's just some particular lattice we choose. And people have known that these kind of constructions can lead you to some statistical models. Basically, we learned these things in these papers. And also Frank's paper. But there are also some mathematicians that worked before them to also argue something. It's named the hate model. So I will first introduce these known examples. So for instance, let's pick the icing category. I just write icing. So it has 3 objects, 1 sigma per psi. And now we want to make it to a two-dimensional Pythagorean function. Then these black lines are the open legs of this 3D object. So we have to fix what these black lines are. So basically, we are for triangles. We just project this leg to. Oh, sorry. We just project this leg to sigma, and we project this leg to some superposition of 1 psi. So people have actually shown that if you impose this boundary condition to that, basically you're projecting these white lines to these objects, then you will get exactly Pythagorean function of the two-dimensional classical icing models. what do you mean by with the icing lines term? So basically, I'm considering about the very. So you have a bunch of spins on some lattice, and its partition function, its Hamiltonian is given by the and ij are the neighboring sites. Basically, just the normal classical icing models. Yeah. So actually, how can we see that? So after we imposing this, actually now these red circles are playing the role of these sigmas here. So it's actually the spin up and down here, and the F symbols together with this particular choice are telling you how these red circles are interacting with each other. So then it will give you the icing partition function. And at the critical temperature, you basically recover the icing, the critical lattice model at the boundary of this topological field theory. So
So this G is essentially the partition function you wrote in the previous page. And the only difference is that you're adapting on the boundary.
Yes, we project the boundary to this. And we are also summing over these red circles as still. And these red circles are playing the role of the spins here.
In what sense this result when you learn in those papers?
In what? So basically, it says the very same thing here. And in these papers, they propose more models to be computed. And they propose not only in this case, also a series of cases. The icing actually is one of the AK series categories. And this is actually the A3. So for any AK, you can do similar things. And you get a minimal model. These are something people already know. Yes, this is already known. Previous page, what do you mean? Yes. Oh, you mean the construction of this TQFT? It's I think it's in the 90s. Yeah, so basically 12-0 says that we can use 6J symbols of groups to make these kind of constructions. Then they generalize to the spherical fusion category. And to make things easier, we are using a unitary fusion category, but as in general, spherical is okay. So now let's try to understand what is happening here. Let's see this by, so below it are our observations. So basically, at two extreme cases, you get the symmetry breaking phases of the icings. But there is some residual sigmas here. So basically here you get 1 here. So basically it means that all the spin are chosen in a particular direction. And here you is a equal weight superposition of 1 psi. And basically it's the that phase of icing. I don't remember the English word. So sorry. So I can write everything in one formula. I want to show this later, but I can write it right now. So basically, every time we see these kind of things, it's equal to F symbol. Yes, and then we put some tensor. Then we put some tensor on it. It also has these labels. And they are tensor together and then sum over all these objects. Then this gives you local patches of our partition functions. So for this particular case, we're just choosing the t to be t sigma sigma 1 to be 1. And here is choosing t sigma sigma 1 equal t sigma sigma plus I equal 1. Is that more clear? So in these two cases, this is a partition function we are actually writing down, local patches of partition function, and then we sum over everything. All others are 0. That is 0. Sorry? Oh, then maybe yellow one.
This diagram here, this whole thing with the blue, the white, the red put together should be understood. It's this product of F and T, you're saying?
Yes, product of F and T, and then we sum over everything.
I think there's a typo right plus psi.
Oh, it's actually the reverse. Yes. T is some boundary condition we're imposing. Basically, I write it into some tensors. So it's actually so it's some number with some tensor with 3 labels, and the same label as these white lines. Sorry.
You wrote down a partition. The strategy here was the Sept partition. You're reinterpreting as Kaixin.
No. So this is for closed manifold. For closed manifold, it's a topological field series. So you can basically change every triangulation and it's still the same partition function. But here, I put it on an open manifold, manifold with boundaries. And I then attach different kinds of boundary conditions to this topological field series, then make it not topological. Yes, sorry, I didn't make that clear. Yes.
We go from a 2 plus 1 dimensional state to 2 dimensions to partition dimension. Exactly, that's what we propose in our paper, is that it can we normalize this, you can start looking for our G fixed points. This is one of the points of the paper.
Yes. So if I'm imposed, if the tensor here is oh, okay. So now I'm writing a general tensor for this partition function. So
yellow circle in the middle, you also assign
It's just representing a tensor. Maybe I should write this. It's just representing there is a tensor here. So to recover this partition function, the tensor I'm going to use is -8, I think, and other 0. So basically, it's just some trivial product state. Basically, you're taking these edges to fix it to sigma and fix this edge to this state. Basically, it's a product state. But we are going to yes, TAB. This will give you the icing, classical icing.
So this beta, introducing the beta is a special case of sandwich the strange correlator.
Yes.
By selecting the other side as some kind of product state.
Yes.
Is that product state for the case?
Yes. In this case, it's a product state. Basically, you are putting only one chosen object on these edges.
So this T tensor does not involve one aside. Is that the consequence of the product state? But in general,
Why do you say it's not? Yeah, but it's actually a very crucial point we are going to make.
in general, you can
Yes, yes, sure. Yes. So we interpolate this.
when you say implied aspect,
Yeah, it's actually a square here. I didn't show. There are two copies of icings, but basically classical icing. But there's a square here
so this partition function is the partition function
of a classical. There are two. So there are two copies of classical icing here. One lives on this. One lives on this lattice, and the other lives on these edges. So how can we see that? So oh yeah, I should say some. Yeah, that's more clear. Yes, thank you very much.
This partition function model for massive and actually detail. I think statistical model.
Yeah, that's not.
Yeah. Yes, statistical classical models. Yes. So we are actually building lattice models that in the infrared they will flow to CFTs. Not we are writing the exact CFT partition functions. Yes.
But actually, what is relevant is indeed all the defect lines of the string net are of course inherited.
Yes.
So you can also create all the defects, all the possible things. You can immediately incorporate them from the string net in your classical partition function.
So that's also why we say that there is some part of the category is enforced on the CFT side. That's what we're claiming. But it's not very it's not in math rigorous. Yes, at inverse temperature beta. Yes. By 2 copies. And then we are thinking about what are these sigmas here. Basically, we are going to use something called the modulus of the the modules of the Frobenius algebras. Before introducing this, let me first say some few words. So basically, these things this thing can be defined as the Frobenius algebra. Basically, it tells what kind of gap phases you have here. So basically, it has the high temperature phase, it has the low temperature phase here. And these are some modules of these algebras. So basically, we are claiming that these two extreme cases actually correspond to the modules of Frobenius algebra, not the algebra itself. It is what makes our construction so successful.
Sorry, explain the appearance of Frobenius algebra in just one sentence better than just I won't be able to understand. Where is the Frobenius algebra?
So I'm going to introduce that step by step. Okay. Before that, I should first say that given the topological bulk inside, every time we want to, it is actually quite hard to, let me write it all up. So basically, we first need to understand what these kind of things actually are doing. So now we are going to use some number equations. So basically, it gives you 2f. And using Penhamel equation, it equals to let me over this. So basically, we can represent the Penhamel equation here in this way. So it's actually also a pattern move in the bulk TFT. But if we write it on the boundary, it's something like this. So what are these going to make to our tensors? So basically, we were doing F move to these tensors. Oh, I shouldn't use. You can understand. I shouldn't use the same color here. So what we are saying is that if we put the tensors here, and then the tensors of the dual of another triangulations here, they are related by this thing. This is just F symbol. So actually, everything we did to the boundary tensors is actually the same as what we did to the categorical diagrams to just as usual categorical diagrams. So here we are doing an F move, so we should multiply it with the F symbol. And we can also have this kind of things. So basically, if you have this kind of tensors, so and we just have some underlying F symbols. It's hard to draw. Is it right? So we can use the unitary conditions to make it actually a straight line. So now we can see that if we know what kind of tensors that are invariant under all these kinds of moves, then it's basically a topological boundary condition. Yes, we need unitarity. So basically, you are having something like this. You have some F, ET. Oh, so this is 2f. Oh, here. No, they have no relations. They're just two different equations. So this comes from the Pentagon equations, and this comes from the unitary equations. The unitary equation basically tells you can remove a bubble, and that as the Pentagon equation tells you can do f moves. Pentagon equation. Oh yeah, sorry, Pentagon equation. Yes. So 2f equals 3f with sum over this new line. Yes, unitary will have symbols. So if I had to write down, it's something like this. Oh, sum over f is delta E prime. Sorry. Oh yeah. Yes. I forget the dagger also at the beginning, so I need to put some dagger here. So basically, what I'm saying is that if I want to relate these two different triangulations, first I need to write the f symbols as new f symbols. Then I need to write my t's as new t's. And what's the relation of the new t's and old t's? From here, we can read out that 2 t's equals 2 new t's with f symbol. So you are actually doing f move to these tensors to get new tensors. Is that more clear? T3s are new tensors. Yeah, new tensors. New. So to make this partition function invariant.
So it looks like you were making that product basically invariant.
Yes. So let me restate my claim. So every time you want to change the triangulation from this to this, and keep the partition function invariant, basically this equation, you then need to enforce these kind of equations to relate to new tensors and old tensors. And these are very similar things. Basically, it says if we have two tensors, they are joined like this, then it just becomes some delta functions. Now we can see that what's the condition for this tensor to be invariant. For this tensor to be invariant under all these moves, basically we are requiring these tensors to satisfy the Frobenius algebras. Yes. Yes, if the new tensor and old tensor are the same, then it's an invariant boundary condition. It's an RT fixed point, basically. It comes from the Frobenius algebra. I'm not so sure how to define the Frobenius algebra, but some people. Yes, I'm now introducing, but I'm not so sure the mathematical way of defining Frobenius algebra. But basically it's. I mean, I may not say the very rigorous mathematical definition of the Frobenius algebra, but I will show that we are constructing some topological fixed boundary condition of our models, and it's related to the Frobenius algebra of the category. So now we want something like this. So basically, it's invariant under F moves. With F here. And also it's these kind of things. And now we see the mathematical definition of spectral symmetric Frobenius algebra. Basically, they say something like this. First, you pick a composite object we call A. Say in the icing case, it's 1 or it's 1 plus psi. Then we need these algebras to form some closed. We need this A to form some closed fusions. Basically, we need something like this. Because it's symmetric, we can actually forget about the arrows. And we fix some tensors here. We fix some, I don't know how to actually put it. So we are fixing how they are fusing together. And then we require that this kind of objects to have these equations. So basically, you're doing F moves to these algebras, and they remain is the same fusion. But it's a mathematical way of saying this. So what I actually did is just we find some tensors we call M. We call it F. So we are saying that we have some object put on these algebra labels, and we are basically requiring that it applies to all the we're basically requiring that these F symbols are symmetric and so on. And also we have equation like this. Sorry. So basically it's F move invariant, and we're also requiring these kind of things. So we're basically restating these topological fixed boundary conditions. I think Zhao Yu has proved that the actual mathematical Frobenius algebra is in one-to-one correspondence to the things we need here. But I'm not so familiar with the proof. I just say that we are using this kind of F tensors to represent our topological fixed points.
But these are even interesting cases. These are the cases that don't give us the CFT.
Yes, if you directly, I'll come to this later, but especially if we just add some F symbol, just add some algebras, we don't get CFTs. We need to include modulus.
Something with zero
Yes, something like GH. Yes. Yes. Yeah, it's obviously it's related to the center. So we are talking about the
category, you define the morphism. Write that triangle graph morphism. You write it in the basis. So that's define the morphification. Then you translate the categorical basis. Say that. No, you don't. No, you don't need grading. There's no grading.
So you're saying this observation is very general. It can work for different choices of strain N, and you have different choices of A. And then here, what you wrote are just two simple examples.
yes. For Kaixin, it has these two Frobenius algebras. I will just say algebras. I don't want to repeat the Frobenius part. So like what kind of more?
There are more. I can tell you later.
Oh yeah, sure. So you mean connected ones or disconnected ones? So of course you can add more disconnected ones, but we are talking about connected ones. So they are stable. They are stable fixed points, but disconnected ones are unstable. Maybe we can discuss later. And so it's not enough. We still need the modules. So by modules I mean we're using the right modules. So in some other object we call it M. And when it fuse with A, it also gives you M. And we also define some tensors here. So now what we are requiring is the following. I require that so two modular can be brought into these forms. And to put it into equations, it basically says that these rows under F moves, they goes to here is a F and here is a row. And with this thing, now we can say that the tensor that we put into the into the boundary of the Kaixin TFT is basically these rows. So rho 1 sigma plus I, let me write the full equations. So when you have algebra, this algebra, we compute F to be these things. And we compute the rho to be, and when we have this algebra, the F is so it's symmetric, so basically we can interchange things. And the modular associated to it is So we also pick the M object to be sigma here. So now we are talking about some tensor associated with this modular specifically. So they are writing at this.
You know that your partition, your state sum is also expressed in terms of these modules?
Yes, I'm going to show that all my boundary states are written in these modular tensors. I will call these modular tensors.
So the different ways in which you can write them.
Yes. And now let's see what's the critical point here in this case. If you remember, the critical temperature is flowing. And if you put it into this it's basically we do a rescale here to make things more clear. So it's actually there's a square here and there's a here, but I rescale it. So it seems kind of familiar to us. It's actually the row of list. I will name it row A equals 1, M equals sigma. And the same here. So basically it's equals to row plus so that is our observation. And we find that if we have some way to normalize this row, then this kind of equation is true for any cases between any frequency algebras, between any module of between any modular tensors. So rho is some tensor that has 3 labels. What I mean is rho is a tensor that has 3 labels.
Okay.
And the only non-zero component for this rho is rho sigma sigma 1 equals 1. And only non-zero component of this rho is rho sigma sigma 1 sigma sigma psi. Yes. And actually, in this case, it's quite easy to see the normalization. You have this 1 plus 1, so you get a square root 2 here. So maybe now I can say, how do we find such strange things? Yes. So first we pick some algebras. Then every algebra has many different modules. Then we calculate out all the tensor rows and first tensor F, then tensor row.
So the first part of the line, you pick your A,
Yes. So you pick. So I should restate all my. So mathematically, given any category C, we can get all these connected frequency algebras like A1, A2, etc. And for every A, we can calculate out some associated tensor F. And from this A and F, we can find some modules of the algebras. And these are all objects. These are objects. And then we find some tensors. And the property of these tensors are given above. Yes, yes. And we are going to need the same modules. Yes, yes, yes. So that's how we cage all these province algebra into local puzzles. Yes. Yes, we just write down some math definitions. Yes, yes. Maybe I shouldn't spend time here. So basically, what I just said is, giving our constructions, we know there are some equations that are forcing the boundary to be topological. And we just write out these topological ones. And all these topological ones are associated to some other tensors. Maybe I'll skip some part. Let's just take an example, so you will see more clear why we came up with all these strange things. So in Kaixin, we are actually putting some sigmas here and some 1% here, and actually it's the same as the A3, where it has 0, 1, 2, and basically what we are putting is 1, 1 in 0, 2. And we actually can have a small series of these categories. We can have, particularly we are considering this category. So now we are trying to put some 2's here, because 1's are already solved out, so we put some 2's here. And it will have some 0, 2, 4 here. And we can just put something like this. We put x plus y 2 plus z 4 here. And we want to find out under these x, y, z's, what this state, what's the infra theory belong to this state. Then we just do some numerical tests. Yes. So it's actually the more refined version of these exercises, but basically we are getting some kind of phase diagrams, and we see many straight lines. Now we want to interpret these straight lines into formulas. Let me put it this way. So started, we don't what should I say? So let me first introduce the RG algorithm. How we get these phase diagrams. So basically, we are doing RG flows to these boundary states, and every time we do our RG, it will, for gap phases, it will flow to some boundary tensors. That is eventually our RG phase point. So so boundary condition, or I can say boundary conditions. Is that more of the topological field series? So basically, how do I impose these? How do I impose these white lines? Yes, we call this boundary. So in Frank's paper, and also before in Yoizhuang's paper, they call this kind of construction the strange correlator. And what is a correlator of what? So basically, there is some. So basically, some F symbols. And they called, okay. So,
The product state. What is the product state that you take the overlap with is the boundary state?
yeah, so basically you fix the, here is the boundary triangles. Remember that when in the icing case, I fix these two to sigma, and I fix boundary. Yes. 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 So I impose in this boundary state particular. So because the fusion of 2 plus 2 only gives you these 3. So it basically contains all the phase space if you fix this.
So you fix 2 and the other.
Yes. Yes. No, now we are considering another category, A5. So, and particular modules. For now, I still don't know its module, but for some fixed. Yeah, I fixed these lines, and I let this line free, and then I calculate some phase diagrams.
And then you have 3 different heating covariant algebra associated with the same model.
So let me do it in the time order. So at start, we just put in some states in our algorithms, and we do RG to this boundary conditions. It will flow to some. Eventually, it will flow to some fixed point. First, we found out that all these fixed points are encoded in the tensors associated with each different Frobenius algebras. It's easy to see because these Frobenius algebra are fixed points of these equations. So now, given this, I can get some phase diagrams. So basically, I can rescale this as the way we want. So I just fix x to 1. So we only have y and z here. We can get some kind of phase boundaries. So as start is some curvy. It should be something like this. If you really write it this way, you will get some curves. But once you take it into this figure, so actually, I'm actually using the z square and y squares here. Then it all becomes straight lines. Then we begin to wonder what happens. And then we come up with all these formulas to say that we are computing some algebras given some modules. So in this case, the algebras we choose are 0, 0 plus 4. This is A0. We call it this is A1. This is A2. There is some 0 plus 2, but it does not have the module 2. So that does not show up here. And also so basically, we get this kind of phase diagrams. And we want to figure out. Yes. Yes. Yes.
That's the only 3?
Connected ones, I think.
So what's the story about the other ones? Like, are those also fixed points?
So if we start with these kind of configurations.
Frobenius algebras emerge naturally from some fixed points, the RG.
Yes, yes.
Which somehow makes sense. Then,
yes.
But what about
So if I really fix the initial tensors of these 2 to 2, then I don't get other algebras. Basically, I only have 3 others. One of these and the other of like this. they don't have, yes. Yes. Yes.
Must be the module, which is something I don't see, but Sept. But are you gonna later? But that's not enough to kill the non-connected. Yeah. So not only not connected, but
Yeah. So basically, we.
You said you're gonna using the algorithm.
How do I put this? So now let's write the general equations then. So our general construction works like this. Okay. So now given all these rows we have, so we have some row that's given by the right modulo of some algebras. This is AM, some row given here. Then first I need to put it in a unit cell. The unit cell is important, but I don't have time to stress why it's important. So I need to consider an overlap of two rows. So basically, I'm putting and this is row, and there are some A, B, E, C, D, A, B, E, C, D. And this is the unit cell we are going to use, the local tensors we're going to use. So basically, first so this is some local tensors. And these local tensors are written in these rows. Now I'm going to add these local tensors to give our construction of the strange correlators. And also we need to normalize it. We normalize it by, and this normalization is also something we work out, but probably I still don't have time to talk about it. So that's a sum of quantum dimension here. Oh, it's dA and dm, but the m is the same, so we don't need it. Yeah, we also need to put a dm here, but m is the same, so I didn't write it. Then we write out all the algebras. So given a C, we can write out all the algebras and write out all the m's. And we choose a particular m and see what kind of algebras is associated to this m. And we write out all these tensors. And we call this a local maybe it's not too right to write it as a state, but basically what I mean is this. Basically, it means these local tensors. And then I pick some m, and I choose my local tensors. This is actual tensor I'm going to use, some t. I want to write it as this. So it has some collection of algebras. And we have some coefficients here. This means I have normalized it. So basically, this thing. So now we claim that for any two algebras, basically, I'm claiming that this kind of things is always a phase transition point, but not always a second order. I will show that what kind of things will brought out more closely to second order ones. And I also say that if you are consider more algebras, and let's say I write some general state C. We claim that large parts of these phase boundaries are given by this kind of C. So basically, the phase transition between A and Z should happen near this kind of states. Okay, sorry. So these states, if you input this, then it's trivially satisfied. And you can add some perpendicular part of it into this C. And it also should satisfy these equations. And this equation should give some parts of the phase transition. Now let's see some numerical results we get.
Here was space that the state A has you see. So you have the lattice on the two dimensions.
So the same as before, I have these triangulations. I have these F symbols embedded here. I have F symbol put here, and I put these tensors upon it. Then it makes some particular functions, leaving only these red circles. If you are only seeing this F part, it's a state. But if I impose in these boundary conditions, then it's just some number.
So you get some tensor.
Yes.
Partition function.
Yes. Yes. So it's the same as before. It's the same as what I said before, but now I. Yes, yes. Yes. Yes, yes. So you can also shift the inner bulk, but we haven't do that. Basically, you can do something to all of them. But it will be harder to compute numerically, but you can do any kind of numerical experiment in general to test what you can find. Basically, you put some defect, you put some excitations, whatever you want. But for now, I just state these isometric cases. It's more easy to compute. And now I will put my phase diagram on something like this. So basically, after normalization, all these AIs, they are just some unit vectors. So I can put 3. So when I include 3 of them, I just plot some ternary phase diagrams. So in this corner, this is AI, this is AJ, this is AK, and this is just the vector given by AJ minus AI. So all these reflect the actual phase space of these vectors, of these tensors I give. And then you will find that these are the Hagroff cases. First, you can see that for any two, say this is A5 and A6, the middle point is where the phase transition happens. And for this case particularly, you can go all the way into the trapezoidal point. But any graph looks like this, but particularly this one is from Hagroff. Yes. Hagroff. So the ones that people wonder if there is a RCFT related to it.
Name of a spherical solution tension.
Yes, yes.
spherical center. This hybrid spherical fusion category is a subcategory.
Yes, I think.
This is the one.
Yeah, I think so. And there are not only this one, but we need more numerical data to confirm all the categorical data, all the conformal data.
Factorizes the CFT doesn't have to, because I guess if the CFT does, then that can't be consistent with what Frank is saying.
No, but so what you're actually doing is something like co-set theory of the double of the Marcus or something. That's what happens. Marcus automatically some relevant operators are kind of added to your theory, such that you're not basically simulating the theory as we want to continue limits, but the lattice adds for some reason that we don't understand, and that's what Leo explains. That flow to another CFT that has like something like such a charge in the order of 2.
But it's possible that this is a modular category that factorizes, but the CFT doesn't, then it doesn't have to be what they're saying.
So basically, I'm confirming through numerics that our claim are basically true. So first, this middle point is just equal a summation of these two Frobenius algebras, and it's the phase transition point. And if we go to the perpendicular direction, it stays in the phase boundaries. So in some cases, it has some curves, and also in the A5 cases. So in many cases, it have some curves, but it's majorly straight lines. So now let me say some words about how we determine the symmetry, determine what the property of the resulting CFTs. So let's again look at the Ising case for the first. In Ising, maybe 5 meters. That I just state these cases. Then people can go and we can discuss later if people are interested. So 1 sigma psi. And it actually has 2 Frobenius algebras. As I just said, it has 1 and 1 plus psi. But the sigma is missing here. So basically, all these Frobenius algebra actually belong to a subcategory of this Ising. It's actually just a Z2. So when we are computing these two, the only object that is left of the resulting CFT is actually from this Z2. So we are claiming that the resulting CFT is described by the center of Z2. So basically, it applies to in other cases. So that will be it. Sorry? So in Ising cases, we only have 2 connected Frobenius algebras. That's the 2 phase we pick, and we let them interpolate to give phase transitions. So their phase transitions is so the thing I want to say is that in between their phase transitions, they actually cannot see the sigma here, because they are both the Frobenius algebra also of the subcategory of the Ising. Actually, they can only see the Z2. So our claim based on this diagram is the resulting Ising CFT. Of course, we know it's Ising. We can only say that it has a subcategory of center of Z2, although actually it has Ising. But I can know from this diagram is Z2. So basically, it's what's going to happen for other cases. We will first figure out what is the subcategory of this, the 2 Frobenius algebras we are computing. And we will see both numerically and physically that their common parents are the categorical symmetry of their common parents are kept in the resulting CFT, but not all the way to the fathers. So basically what I'm saying is this kind of things. You can pick a very, very giant category and it will all the way to some subcategories. If you misfortunately pick some Fourier algebras of this, they actually belong to this subcategory. Then the resulting CFT only has the property of this subcategory. They do not reflect your parent. That's actually so subcategory. So basically, you can only see the or you can say condensate to a small category. Okay, so I will say just subcategory. Yes. Okay, I will close it. Sorry for the delay.